The same equations that predict black holes also predict something else, an object that does the exact opposite. Nothing can escape a black hole. This other object is the reverse. Nothing can enter it at all. Physicists call it a white hole. And the strange part isn't that it's fictional. The math says it's just as valid as the black hole you already know. And some physicists now think every black hole you've ever heard of might secretly be building toward becoming one. In 1916, physicist Carl Schwarzschild found the first exact solution to Einstein's newly published equations of general relativity, describing what we now call a black hole. But when mathematician Martin Kruskal fully extended that same solution in 1960, mapping out every region of spacetime, the equations actually allowed, he found something nobody expected. The maximally extended version of the solution didn't just describe a black hole. It described 4 connected regions of spacetime: our universe, a black hole, a second, separate universe, and a white hole. In 1964, Soviet astrophysicist Igor Novikov took that mathematical curiosity seriously enough to propose it as something that might actually exist in nature. A region of space where matter and light can only ever come out, never go in. There's an even stranger detail buried in Kruskal's original map of this spacetime. The black hole and the white hole aren't just 2 separate objects. In the fully extended solution, they're connected to that second universe through a bridge, a wormhole, technically called an Einstein-Rosen bridge. After Einstein and physicist Nathan Rosen first described this kind of connection in 1935, years before anyone realized it linked to a white hole at all. The catch in this classical picture is that the bridge collapses faster than anything could ever cross it, making it a connection you could theoretically map, but never actually use. Picture a black hole in reverse, frame by frame. Instead of an event horizon that only lets things fall in, a white hole has an event horizon that only lets things out. Approach one, and no matter how you try, you can never cross into it. You just keep getting pushed away forever. Like watching a black hole's collapse played backward in time. For a while, physicists took this seriously enough to wonder if white holes might explain quasars, the extraordinarily bright, energetic objects astronomers had just started detecting in distant galaxies in the 1960s. Quasars were at the time deeply puzzling. Point-like sources outshining entire galaxies, pouring out more energy than anyone could easily explain. If a white hole were expelling matter and energy from some hidden source, it might look from a distance exactly like one of these puzzling objects lighting up the early universe. It was a serious enough proposal that Novikov and physicist Yuval Ne'eman explored versions of it independently around the same time. We now know quasars are actually powered by supermassive black holes, not white holes. Matter spiraling into an accretion disk around the black hole heats up so intensely before crossing the event horizon that it radiates enormous amounts of energy. But for a brief window in the history of physics, a white hole was a genuinely competitive explanation for one of the brightest objects in the sky. Then, in 1974, physicist Douglas Eardley showed why that idea probably doesn't survive contact with reality. Even the tiniest disturbance, a single stray particle, a whisper of gravitational interference, would be enough to collapse a white hole into an ordinary black hole almost instantly. Think of it like trying to balance a pencil perfectly on its tip. The mathematics allows it, but any disturbance at all, however small, ends the balance immediately. That same year, physicists Yakov Zeldovich, Novikov himself, and Alexei Starobinsky showed a second, independent problem. Quantum effects near a white hole's horizon blow up mathematically. Another sign that anything shaped like a classical white hole simply can't hold itself together for long. For decades, that seemed to settle it. White holes were a mathematically valid curiosity, a strange twin born from the same equations as black holes, but not something anyone expected to find floating in actual space, stable enough to ever observe. Then loop quantum gravity gave the idea an entirely new life. Beginning around 2014, physicists Carlo Rovelli and Hal Haggard proposed something that reframed the entire question. In classical general relativity, a black hole collapses forever, crushing everything into an infinitely dense singularity. But classical general relativity is known to break down at exactly that point. It's not built to handle the extreme conditions inside a black hole's core. Quantum gravity might behave differently. Rovelli and Haggard's proposal, refined in later papers through 2018 and 2019, suggests that once a collapsing black hole reaches a small enough size, quantum gravitational effects could cause it to bounce, tunneling in a sense, into a white hole, releasing whatever fell in a sudden burst outward. This isn't a black hole exploding at the moment of formation. According to the model, the transition would take an enormous amount of time from the outside perspective, potentially longer than the current age of the universe, even though very little proper time would pass for anything near the black hole itself. Rovelli named the compressed, not quite singular object at the center of this process a Planck star, matter compressed to the smallest meaningful size physics allows, rather than compressed to an actual infinite point. Here's why physicists outside pure curiosity actually care about this idea. It offers a possible answer to one of the most famous unsolved problems in physics, the black hole information paradox. If everything that ever falls into a black hole is genuinely lost forever when the black hole evaporates, that violates a fundamental rule of quantum mechanics. Information isn't supposed to simply vanish from the universe. If black holes eventually tunnel into white holes instead, whatever fell in could, in principle, come back out. Preserving the information physics insists has to go somewhere. In 2023, Rovelli published a popular science book titled simply White Holes, describing this scenario for a general audience. Every black hole you've ever heard of might not be a permanent one-way trip, but the first half of a much longer story, one that ends unfathomably far in the future, with everything that ever fell in coming back out somewhere else. There's a wilder version of this idea that some physicists take seriously as a genuine hypothesis, not just a thought experiment. What if the Big Bang itself was a white hole? The observable universe began from an incredibly hot, dense state and has been expanding and releasing matter and energy ever since, which is, structurally, almost exactly what a white hole does. Physicist Nikodem Poplawski has explored versions of this idea mathematically, suggesting our entire universe could have emerged from the white hole side of a black hole formed in some other, larger universe entirely. Under this framing, everything we can see, our entire observable universe, could be the outflow of a white hole whose interior we're still, in some sense, living inside of. And every black hole we observe forming today could be quietly seeding a new universe of its own, invisible to us on the other side. Nobody has detected a confirmed white hole. Every candidate ever proposed has either been explained by something more mundane, or remains too speculative to count as evidence. That hasn't stopped serious physicists, working in serious peer-reviewed journals, from taking the underlying question seriously. Not whether white holes are useful science fiction, but whether the same physics that gave us black holes was always going to demand their exact opposite too. We've spent so long trying to understand what happens when something falls into a black hole that it's easy to forget the same equations were quietly asking a second question the entire time. Once something falls in, where, if anywhere, does it actually go? Maybe nowhere. Maybe the instabilities really do win. And every white hole ever proposed collapses before it can matter. Exactly as the classical mathematics predicted back in 1974. Or maybe Rovelli is right. And the black holes scattered across our galaxy right now are simply very old, very slow fireworks, still waiting, on a timescale longer than the universe itself, to finally go off. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe, because next time we go beyond again.